Hello, my name is Alp. I'm studying electrical and electronics engineering at Bilkent University. In this video, I will present my Physics 101 lab project, which is about measuring the spring constant in both single and combined spring systems. In this experiment, I observed how the spring constant behaves when identical springs are connected in series and parallel. The required equipment for this experiment includes 4 identical springs for different masses, a stand, a balance, and a ruler. First, in part A, I measured the masses using a balance. I repeated this process for 4 different weights. Then I measured the initial length of the spring, which was 3 cm. I attached a 200 gram weight to the spring and waited until the system reached equilibrium. The force for each case was calculated using F equals mg, where the gravitational acceleration g was assumed to be 9.8 meter per second square. After that, I measured the final length of the spring and calculated the displacement. I repeated this process for all 4 masses and recorded the results in a table. Using Hooke's law, I calculated the spring constant k for each case, and then I computed the average k value to improve the accuracy and precision of this experiment. In plot 1, we can observe that the correlation between force and displacement is linear, and the slope of this line gives us the average k value, which is 266 Newton per meter. In part B, I investigate how spring constant changes when multiple identical springs are connected in series and in parallel. As you can see here, I first measured the initial length of the springs before any weights is attached. Then I hang a 350 gram mass and waited until the system reaches equilibrium. After that, I calculated the displacement. Here you can see the displacement values I measured for 2, 3, and 4 springs connected in series. Based on these values, I created the graph showing how the spring constant changes with the number of springs in series. As seen in the plot, the spring constant decreases as more springs are added, which is consistent with the theoretical model. After completing the series measurements, I moved to the parallel setup. As shown here, I arranged springs side by side and repeated the same method to measure the displacement and calculate the spring constants. Here are the values I measured during the parallel setup. Again, I used the same mass to ensure fair comparison. This plot shows the trend for parallel connections. As expected, the spring constant increases as more springs are added in parallel, confirming the theoretical prediction. The observed values are then compared to the theoretical ones. The expected spring constants were calculated using the average k value obtained in part A. The differences between observed and expected values are mainly due to the measurement errors, such as misalignment of springs or inaccuracies in reading the displacement values. Although there are some small errors, the lines in the plots do not pass through every data point. The overall trends match the predictions, and the experiment clearly demonstrates the behavior of spring combinations. In conclusion, the experiment clearly showed how the spring constant changes in both series and parallel setups. The results were consistent with the theory, despite some small errors in measurements. Overall, it was a successful demonstration of Hooke's law and spring combinations.